Hi everyone, please note that we'll be starting this session at 12:30 as there's a delay in the previous session, so please bear with us until then. Hi everyone, sorry for the delay. So we will now commence session 4C, which is on natural language processing, and the session chair for this session is Dr. Dinusha Tilline. She's a senior lecturer at University of Colombo School of Computing. She obtained her BSc in Computer Science degree and her PhD, specializing in natural language processing from University of Colombo School of Computing. Her research interests are natural language processing, artificial intelligence, and human-computer interaction. So, Dr. Tilline, I would like to hand over the controls of the session to you now.
Thank you, Dashani. So, good afternoon, everyone. This session was supposed to start after the session 4A. Finished this session before the keynote speech. So, in this session, we have 4 presentations, and the presentation is on ID 99. The paper title is Low Resource Sinhala Recognition Using Deep Learning, and the author of the paper is Ms. Hirunika Karunatilaka, and Hirunika will be presenting the paper, and Hirunika received her BSc on Colombo School of Computing in 2020, and she currently works as a software engineer at GVO Australia Private Limited, and her research interests are natural language processing and deep learning, and her current research focuses on developing speech recognition system for Sinhala language using deep learning approaches. So we will first watch the video and move on to the Q&A session. Okay, so we will watch the
I'm Hirunika Karunatilaka from University of Colombo School of Computing. Today I present my research on low-resource Sinhala speech recognition using deep learning. So let's begin with an introduction to speech recognition. What is speech recognition? So simply it is our spoken speech is converted to a text. So according to the analytics, 87% population speaks Sinhala in Sri Lanka, and it is the native language of majority of Sri Lankans. But however, we don't have an open source speech recognition applications for Sinhala. If we do have a robust open source recognizer, we could have increased the performance of our local systems, and as well as we can get the services of the popular applications in the world. So here are the research objectives. So first is to come up with an optimal ASR system using the deep learning approach. Secondly, it is important to compare the performance of the designed deep learning models with the existing standard methods. Last of all is to evaluate and discuss on the recognition accuracy of the deep neural network models. So the main research question that is addressed in this research is finding out a deep neural network architecture that performs well for the Sinhala speech recognition. So let's move to the literature review and related work. So there are different approaches that have been used for ASR since past. From them, a statistical based approach was the state of the art until deep learning comes to the field. Currently, the neural network architectures are the so-called state of the art technology. Therefore, our research also, we will focus on the neural network based approach. So here, there are two main deep learning approaches. In the first one, deep learning is used for training along with the hidden Markov models. In the second one, in the end-to-end deep learning engine, so which is popular nowadays, it is purely based on the neural architectures. So So, but the problem is its performance is based on lots of data and computational power. So here I have included some research work related to different languages and the observations made by the authors. So the first one is done for the Russian language, and there the observations are the number of D players has only a slight influence on the recognition results when you have a low data set. And the second one has done for the French language. There the authors have observed a higher classification and generalization using the deep neural networks. So the research, these researches has been done for the Turkish, Bangla and Assamese, which are low resource languages. But the observation is only a small improvement over the statistical method. However, the authors have not experimented with different neural architectures other than the regular multilayer perceptrons. Let's move to the research design. So this diagram shows a descriptive architecture of the system. So as you can see here, the input to the system is the speech signal or the audio. So then the audio features are extracted into a feature frame vector. So then they are fed into the deep neural network model. From there, the DNN model do the frame classification, and its output layer returns the posterior probabilities for the phones. So these posterior probabilities are then converted into a sequence of phonemes using the hidden Markov model. So the box in red dots presents the acoustic model of the ASR system. So it comprises the DNN model and the HMM model. So the sequence of phonemes that are derived using this acoustic model are classified into words using the language model along with the lexicon. So this diagram compares the statistical GMM-HMM model with the hybrid approach that we are following in this research. So as you can see, the only difference is that the Gaussian mixer model is being replaced by the DNN. So to illustrate the DNN-HMM model, let's have a closer look at it. So the left side diagram shows our acoustic model. So here we do not train the DNN model immediately from the utterance level transcriptions, since deep neural networks requires a good initial approximation, and also the fact that we don't have a human annotator to label the audio chunks to its phonemes. So rather we use a statistical model to produce these annotation via forced alignment. So therefore, as the first phase of the acoustic modeling, we train a statistical model and get the phoneme to audio alignments. So then the DNN is bootstrapped using them. So let's move to the implementations and results section. So I have break down the process into three main parts. My first concern is about the data preparation, which actually requires a certain amount of time because the rest of the pipeline highly depends on the validity of this step. So the speech corpus was collected from the UCSC LTRL, and it contained audio recordings from 50 females and 20 males. So this speech data were then pre-processed by removing the duplicates and missing values. So the next major step is to generate the lexicon. So in this project, we have used a grapheme lexicon, and it contains over 220,000 entries with one unique grapheme sequence per word. So the lexicon was created using the transcripts of UCSC LTRL, phonetically balanced corpus, and the extracted Sinhala words were encoded to English letters. For that, we used the Sinhala Subasa project and modified the code as per our requirements. The final step with data preparation was the language model. We used a trigram model, and for that we used the SRI language modeling toolkit in Kaldi. To ensure the validity of the experiments, the transcriptions related to the test data set were excluded from the text corpus. So moving forward, so after the data preparation, the next step is to implement the statistical model, which is the GMM-HMM model. So as I previously mentioned, the alignments from this system is really important to move forward with the neural network trainings. So here is a block diagram of the acoustic model in a statistical approach. So we have to first train the monophone HMMs by giving the speech data and its phonemic strings. So these monophone HMMs actually depends only on the contextual information of a single phoneme. But on the other hand, the triphone HMMs represent the phoneme variant in the context of two phonemes, typically preceding and following. So we then conducted up to 3 training passes with triphone HMMs. So let's see the results gained from this. So let me quickly explain what is the word error rate means. So it is the standard scale that we use to measure the performance of our models. So the lower the word error rate means higher the accuracy. So from this table, we can see the lowest word error rate is 42.64, and in the left hand side corner you can see the parameter settings that used for that model. So now that we have gained the alignments, we then move to train the neural networks. Here, here are the 4 types of network that we trained in our research. So let's move to the first one, which is pre-trained DNN model. So here the pre-training means before we train the feed-forward networks, we apply an unsupervised training process to the training data. So the only difference from the standard neural network is the starting point in parameter space will be obtained after this unsupervised pre-training. So the reason for experimenting with these models is, according to the literature review, so the authors have observed by using this pre-training, it reduces overfitting, which is important when we work with a limited training dataset. So the next slide will show you the results we achieved for the models after several training passes. So as the chart shows, the lowest word error rate has been decreased up to 39.92. So when analyzing the improvement over the statistical model, it is 2.72. However, there were also some drawbacks, like it needs extra hyperparameters. So we need to first do a RBM training, and also its computational time is also larger. So then we thought to get rid of the pre-training process and train and move with a regular multilayer perceptron. So unlike in the pre-trained DNN, here the weights are randomly initialized. So the lowest word error rate was 39.69. So that was somewhat better than the earlier models. So when compared with the statistical model, this has an improvement of 2.95 and a minor improvement of 0.23 than the pre-trained model. The next network type was the time delay neural network. The Kaldi toolkit supports 2 types of TDNN networks. The network type 1 is a typical TDNN, and the network type 2 is a factorized form of TDNN, which has been introduced by Daniel Poway, so who is also the main developer of the Kaldi toolkit. So, and we experimented on both of these network types. So the results are like this. So as you can see, the lowest word error rate was 35.16. So, and if you look closely, it is noticeable that the lower word error rates have been gained when using the second network type, which is the factorized form. When analyzing with the previous models, so there is an obvious improvement to be seen. So, and the other significant fact is it took very low decoding times compared to the other models. So the final network structure we experimented on is the time delay neural networks along with LSTMs. So in this network, so we stacked a LSTM layer on the top of time delay neural network layers. So we'll see now the results gained from this type of model. So we could observe the lowest word error to be as 35.87, and it was obtained by stacking the LSTM layer on top of the model which earlier gave the lowest word error rate, which was 35.16. However, it did not surpass the performance of that model. But this obtained a 6.77 improvement over the statistical model. By looking at the chart, we can see that the lowest word error rates were observed by the networks using the time delay neural networks. So let's move to the evaluation of all the results. And I would like to show you some audio files translated by the 5 models which achieved the lowest word error rates. So here is one. So the red text indicates the incorrectly identified words while the green indicates the correctly identified words. So as you can see, there are more incorrectly identified words when comes to the baseline GMM-HMM model. So here is another sentence. So here a significant performance is shown from the time delay neural networks as they have been able to identify the word with the correctly. So all the other 3 models have been failed in that point. So when analyzing that, we found, so in the text corpus, the phrase with the is not followed by any suffix that is relevant to this sentence. So however, the phrase with the is followed by suffixes such as yak, karu, karuange and karuge in several times. So it proves that this time delay neural networks is good for finding the wider temporal relationships even with a low data set. So, well, that brings to the end of the results evaluation. So let's move to the conclusion. So we obtained a ASR system for Sinhala with a word error rate of 35.16, or in terms of accuracy, it is 64.84. The factorized TDNN setting was identified as the best performed network type. So furthermore, it can be concluded that deep learning approaches perform well for the single ASR, even with the limited dataset, because we could achieve a 7.48 of improvement over the statistical model. So finally, it was observed that if we can extend the text corpus along with more training data, so the models are able to identify most of the words correctly. Since I am nearing to the end of the presentation, I'll briefly go through the future words. So we can experiment on the factorized time delay neural networks by setting different configurations and concatenating them with other network architectures. And also, to increase the accuracy, we can use a more extensive corpus with a phonetically balanced vocabulary. So those can be considered as our future works to this research. So with that, I am finishing my presentation. Thank you.
Okay, thank you, Veronica. So now is the time for the Q&A session. So anyone has any questions, you can raise them. Okay, so I will lead with the question. So Veronica, do you know what is the state-of-the-art deep neural networks that were used for this speech recognition?
You mean, madam?
Yeah, so you have used several deep learning networks in your experiment. So what is this? What is the most popular one normally used in speech recognition?
Basically, for like languages like English, they have used this LSTM1, and also some have used this time delay neural network.
Okay.
But from the results, actually the LSTM one was the one that has given the good results. But in our research, we actually experimented with a one LSTM layer. But then the results were actually somewhat lower than the time delay neural network.
Okay, so have you found any other research that with the same case where the time delay neural networks performs better than the LSTM?
No, actually, madam. Most of the ones have only experimented with one architecture. Like if time delay neural networks, so they have experimented with those things. Couldn't find like a comparison between them from one research.
Okay. So if you have any other questions from the audience. Okay, it seems there are no other questions. So we will thank you, Veronica. And so we will show our appreciation for her by unmuting her microphone and giving her a round of applause. Okay, thank you. So we will move on with our next presentation. So the next presentation is on paper ID 101. And the paper title is Exploring Neural Machine Translation for Sinhala Tamil Languages Pair. And this paper is presented by Ms. Sumudu Nisanka. And Sumudu received her BSc Honours in Computer Science from University of Colombo School of Computing in 2020. And currently she is a software engineer at WSO2 Lanka Private Limited. And her current research interests are in areas of natural language processing, deep learning, and web services with APIs. So we will move on to her recorded presentation, and we will continue with the Q&A session.
Hello everyone, today I am going to present the research paper with Exploring Neural Machine Translation for Sinhala Tamil Language Pair. Before moving to the topic, I would like to give some brief introduction regarding the machine translation. Then, the machine translation refers to fully automated software that can translate source content into target language. Humans may use machine translation to help them render the text and speech into another language. Machine translation tools are often used to translate vast amount of information involving millions of words that could not possibly be translated in traditional way. Usually refers to platforms such as Google Translator, Bing, Yandex, and Naver. The talking about the motivation behind the research is Sinhala and Tamil are the national languages in Sri Lanka. So most of the people use these two languages for their community. But most of are fluent in one language. Because of this, communication gap may increase. Through this research, we will be able to contribute to make effective communication in between Sinhala Tamil communities. And the Sinhala Tamil language have low number of unique words with large vocabulary. That means both are more politically rich language. Talking about the background and the related work, here is the flow that I used to do my background research and the related work. First, I needed to check whether there are research for based on neural machine translation. So yes, of course, there are so many research I found using this approach. Then I motivated to find the research which do for more politically rich language. As a third step, I needed to observe that there are any research for low resource language. In the fourth area is the area that I do focus in the background research because these steps are given most valuable to our research. This diagram shows summary of the main area which I mentioned in the previous slide. It is Tamil Sinhala translation from neural machine translation. As usual, we can categorize this translation under the three approach. One is supervised, unsupervised, and semi-supervised. In the green color area, I used to represent the neural machine approach, which is already taken for single Tamil translation. And the orange color area is showing the areas we are going to address through our research. The mainly another thing, collecting parallel corpus is very hard, especially raw resource language is getting so many hard. So we are focusing to do our research only using monolingual corpora data, because monolingual corpora data is available in publicly and we can collect it easy rather than the parallel corpus data. Then after analyzing the research background research and the problem statement, I was able to come up with these research questions. One is the best approach for achieving high accuracy in single Tamil translation using only monolingual corpora. Second one is what is the effect of the monolingual corpora on the translation accuracy. And then the research design, the first research design is, you can see here, this is the diagram, high level diagram, and using only monolingual corpora data. We use data pre-processing and do some deep neural network architecture for use to train the model and evaluate based on the blue score. Here is the second research question we are going to address. Use the both parallel and monolingual corpora data. We use back translation to increase the data set and deep neural network architecture for training the research data set and evaluate based on the blue score. Then evaluation is mainly based on the blue score. It is score to compare the translation with given reference. The matrix ranges from 0 to 100. Then the result and the analysis. The first stage, we did feasibility study for checking whether we can collect monolingual corpus data. So we write Python script and I was able to collect in the 1,000 sentences per day. So now detail regarding the data corpus used for our research. Parallel corpus data with 25,000 sentences with Sinhala and Tamil, and monolingual corpora data is with 10 million word corpus in Sinhala and 4 million word corpus in Tamil. Then we needed to address the morphological richness of the Sinhala and Tamil language before doing the research. So we used byte pair encoding for word segmenting technique. And through this technique, we can identify the rare words. Here is the representation of the Sinhala word after applying the byte pair encoding and representing in the Tamil sentences. Then I took our parallel corpus data for analyzing the byte pair encoding behavior with words. You can see the out of vocabulary ratio in the full word form data set. In Sinhala it's around 20 and Tamil it's around 30. Then after applying the byte pair encoding for the parallel data set, you can see in the red color area, the unique number of data words is decreased and the total number of words is increased. Due to this factor, the out of vocabulary percentage getting 0. Then we conclude that byte pair encoding can use for reducing the morphological richness of the words and can address the issue with rare words. Then addressing the first research question, what is the best approach for achieving high accuracy in Sinhala Tamil translation only using monolingual corpus? Then here we use only monolingual corpora. Then we needed to do some data pre-processing for monolingual corpora data because it's known as unlabeled data. Normally neural network need labeled data set for training. For we use word embedding technique for data pre-processing to make alignment in the monolingual corpora data. Word embedding is a set of language modeling and feature learning technique in natural language processing. In word embedding, the one-hot encoding is a representation of categorical variable as a binary vector. You can see it here. There are problems with one-hot encoding when representing the word in the word vector matrix. It takes alphabetically order. Then sparsity is another issue, which means it takes a lot of space when they are going to store the data. There are two types of word embedding methods. Both word-to-weights and fast text can address the above-mentioned drawback in one encoding. We use fast text embedding method because word-to-weight has the biggest challenge to identify the rare words that are not in the training dataset. Fast text breaks the words into several engrams and subwords instead of feeding individual words into neural networks. It might be useful approach for segmenting the morphologically rich language Sinhala and Tamil. Then here is the orange color area is representing all the approach we taken in fast text. The visualizing semantic and the syntactic relationship between the words using full word form. We use finding out the similar word representation using Rate. You can see there are so many similar words with this result. Then after applying this word embedding, we train this dataset using this deep neural network model. This architecture is used to decode with a recurrent neural network and one shared encoder with bidirectional recurrent neural network. After training the model, we come up with the source sentences like this way. Here is the output that gained from the trained model. You can see so many out of vocabulary tag with output sentence. To overcome this problem, we used byte pair encoding with word embedding. Then after applying the byte pair encoding, we put the similar word Rate. Here is the representation of semantic relationship with word Rate with designation. That means when we have word Rate, we can predict the next word as a Rate, something like this. And then another representation of the word embedding in the male-female relationship. We choose the Amma as our similar. To example, you can see when we have Amma, there is a male-female representation with Tata also there. Then after training the model, here is the sample test that bring from the data set. I selected the second research sentences for further analysis. Although this sentence is incorrect translation of the reference sentence, it shows the correct alignment of meaningful single sentence. Through this observation, we can conclude that there is availability of developing the translation in between Sinhala and Tamil language pair using only monolingual corpora data. Based on this clue, we wanted to check what would be the effect of the translation accuracy when it used both monolingual and the parallel corpus data. Through our second research question, we address this. Then the second research question is what is the effect of the monolingual corpora in translation accuracy? Here we use both monolingual and parallel corpus data and use back translation to increase the data set and create the new data set and do some deep neural network for training the model and evaluate based on the blue score. For when we are going to selecting the deep neural network for a training, firstly we choose recurrent neural network. Then recurrent neural network, the first word is converted into the word vector and it encoded. After encoded it applied some hidden state to encode it in and create new hidden state. When after that it passes into the next word, then add the hidden state to the next word. Likewise, it is repeatedly happen until the end of the sentences. Then after the coming to the final hidden state, it sent to the decoder and convert the target language. Likewise, it is happening in the end of the target sentences. The problem here is that the decoder has to wait till the encoder finish its work. As a solution, attention model is introduced in the researchers. Then in the attention model, all the hidden states are stored in the one hub and decoder can access any time through the hidden state from this hub. Then for this architecture, decoder don't wait until the encoder finish their tasks. So as advanced version of the attention model, the transformer architecture is introduced by the researchers. The goal of this architecture is parallelization of the sequence seekers and reduce the sequential computation. For our research, we use long short-term memory network and attention transformer architecture for doing the research. And then, firstly, we use parallel corpus data to selecting the deep neural network in between transformer and long short-term memory network. Then you can see here, when we increase the data set, the both architectures perform increase their blue score. Then here is the blue score, you can see. Then the transformer architecture perform well rather than the LSTM architecture. Then the blue score can't check the synonymous correct sentence. It only can check the similarity of the sentence. So we need to do manually check the similarity of the sentences. Then here I bring some example sentences that taken from the data set, comparing the same sentence with LSTM and the transformer architecture. Here I bring the third sentences for, you can see these synonymously correct rather than the LSTM architecture. So we can finally we conclude that to use transformer architecture for our further research. Then we need, that time we using the parallel corpus. Then now we using the monolingual corpus data with parallel corpus data. Then we needed to increase our data set. We suggested transfer learning architecture and monolingual word embedding, data augmentation, transliteration, back translation as our increasing technique. In here we choose back translation technique because the transliteration cannot happen used to single Tamil translation because they are not similar pronunciation. Then the back translation, we take the original parallel corpus data and do back system train on the corpus. Then after that, we take the target site monolingual sentence and translate it into the synthetic source sentence, side sentence. Then we have some synthetic parallel corpus data. We add these synthetic parallel to the original corpus and create new data set. Likewise, we did 1 to 1, 1 to 2, 1 to 3 ratio with adding new parallel data set to the synthetic parallel data set to the data set. Then you can see here is the Tamil to Sinhala translation is performed well rather than the Sinhala to Tamil translation, because naturally Tamil language is more politically rich rather than the Sinhala language. Therefore, it performed well in blue score in translation when Tamil to Sinhala translate. And then you can see the blue score, how the blue score behave with the when we increasing the data set. And we are going to do the synonymic analysis also there. Here is the source sentence and the output sentence we gain through our suggested architecture. And we wanted to check our suggested architecture is working through the result with out of domain. Here is the out of domain result. You can see it shows the promising result with the out of domain also. And then overall approach we take for this section 2 is in here. Then the result analysis of the section 2 using byte-pair encoding segmentation leads to identify the rare words, and the transformer architecture perform well rather than the LSTM architecture. Applying back translation technique is able to increase synthetic parallel corpus data and the blue score. The Tamil to Sinhala translation perform well than Sinhala to Tamil translation. Then talking about the overall discussion in the research section 1, we although our approach through the monolingual corpus data can use for developing single Tamil translation, and there is a probability to use the only monolingual corpus data for translation. In second research section, we come up with the applying the byte pair encoding can help to reduce the out of vocabulary, and increasing the corpus size may affect of the performance in the translation, and the transform architecture perform well rather than the LSTM architecture. Using the back translation technique can be increase the parallel corpus from all lingual corpus data. Then here shows all the approaches we took through our resource, and orange color area shows the promising result with suggested approach.
Okay, thank you, Sumudhu. Can you please switch on your video? Okay, so now it is the time for the Q&A session. So if any of you have questions for Sumudhu, you can ask. Okay, so Sumudhu, I have one question. So that you said that Tamil to Sinhala translation is performing better than Sinhala to Tamil translation, and you said that it is because of the morphological richness of the language. Are there any studies done for other language pairs like this one? Say English to French. So is the performance for English to French translation is better than French to English, something like that? Have you studied? Are there any studies? Have you come upon?
Hello. Hello, madam. There are some research regarding the morphological richness, and both those are present in better in morphologically rich language to low morphologically rich language, and we found in Sinhala to Tamil one also.
Okay. So, and also you said that the transform architecture is performing better than the LSTM architecture. So, do you find any reason for that? Why is it performing better with other languages also?
Yeah, madam. There was research regarding by comparison with the transform architecture with the LSTM architecture. There is a problem with LSTM architecture is it cannot bear a long memory. But when come to the transform architecture, that is not a matter because it do the parallelly all the decoding and encoding things. Then recent research found from Sinhala to English and generating Sinhala to English and English to Nepal data set from most recent research. I think.
Okay. Okay. So, any other questions from the audience? Okay, so thank you, Sumudhu. So I think we will show her our appreciation by a round of applause. Okay, so thank you. So we will move on with the next presentation. So the next presentation is on paper ID 106. And the paper title is Lip Synchronization Modeling for Sinhala Speech. And the presenter of this paper is Mr. Chashika Veeratunga. So Chashika received his BSc Honours degree in Computer Science from the University of Colombo School of Computing in 2020. and he currently works as a software engineer at WSO2. And his current research interests include natural language processing and machine learning. So we will move on with the recorded presentation and later the Q&A session.
Welcome everyone. I'm Jashika Veerathindra from University of Colombo School of Computing. Today I present my research on lip synchronization modeling for single speech. Let's start off with the introduction. Let's get to know what lip synchronization is. It is the process of synchronizing the movement of our lips with the sound of our speech. So I have included here two GIFs. In the left hand side one, you can see that in the real speech, it is automatically synchronized. But as you can see the right hand side cartoon, it's just only opening and closing the mouth movements. So no synchronization at all. Let's see what facts motivates us to do this research. First, this technique makes characters realistic, so it can be used to build lip sync models for industries such as gaming industry, film and cartoon animation industry. And the other fact is that the lip synchronization is not a very expensive technique compared to other alternative techniques such as motion capturing. So this was a plus point research on lip synchronization. Here is another practical example of lip syncing. People who are not deaf but can understand speech through lip reading. Imagine a deaf person has an application which has a lip sync model. So audio waves can be converted to the lip movement from the model. Through lip reading, the deaf person can understand the audio waves. I think it's better to get some basic knowledge on the research field. And the phoneme is a sound unit. Using that, you can distinguish one word from another. The voicemes is actually the visual representation of the phonemes. Here's a voiceme representation for the respective phonemes. The special thing about this is there can be one or many phonemes for voicemes. So let's see the research questions that are addressed in this research. There are three main questions. First, we need to find out a voiceme's alphabet for the sinhala, and then have to address what kind of method will be suitable for the generate the voiceme sequence from the sinhala text. Finally, we need to find proper approach to generate the speech animation. Let's move to the aims and objectives. To address the above mentioned research questions, our research objectives will be: first, create a visual speech dataset for the single language. Secondly, extracting the abstract lip shape from the video and discover a mapping from the single pronunciation to voicemes. Finally, to generate the speech animation. When speaking about the research scope, in this research, we are not going to address modeling of facial emotions and expressions of the speech. So let's move to the related work that has been done in past years. There are different categories of research that has been done to achieve the lip synchronization models. The voicemes mapping is the one of core part of these researches. In voicemes grouping, they usually use some algorithm like clustering IDP to the face extraction, and they have conducted research for different languages such as Chinese and Persian. In overall, there are three main approaches to generate the speech animation models. The first one is the static voicemes approach. Here I have listed down two research, and main problem is this approach is difficult to handle the issues with coarticulation. Second approach is dynamic voicemes approach. For this method, I listed down one related work, and it has handled the coarticulation, and it has used active appearance model for face extraction and used 10-hour video dataset. Third one is a state-of-the-art method, which is deep learning approach. This model has got more accuracy than the previous model, but the problem is it needs a lot of speech data to process the model and get the result. So let's see the research approach we have followed. Actually, my initial plan was to experiment on both these approaches and compare each other. The first one is deep learning approach, and however, it was terminated at the middle due to not having enough resources. Then I moved to the second approach, which is static voicemes approach. But however, I will describe the process I followed in the deep learning approach in brief. This is the initial approach that I had planned to conduct as a deep learning approach, but unfortunately, I had to terminate this method. Here is the reasons for the termination. Labeling video frames with phonetically annotated words are really hard since there are no tools available for the Sinhala language. So also recording at least 10-hour video sentences in a studio environment is also a hard task because I terminated this approach. So the main research approach is the static questions approach, which I followed throughout this project. So let's move to that. Here I have included the high-level flow of this approach. So we will look into this step one by one in coming slides. First step would be generating the video data. For that, we recorded video clips so as to contain the overall phonemes alphabet in the Sinhala language. When recording, we only recorded the frontal view of the face and the speaker used the neutral speaking style. So altogether, we recorded 40 video clips. After generating the data, the next process is extracting the features from the still images. We use the active appearance model for tracking the speech articulators. So as you can see, the shape of this face can be denoted by a mesh. In the mesh, vertex location are denoted in red dots. In the frontal view of face, 68 vertices can be identified using active appearance model. For this research, since we consider only the movement in the mouth area, especially in the lip area, so we can focus on the vertices in the this mouth area. According to previous research that has been done by Rong, we can identify 4 main lip features by calculating the distance between some main vertices in the lips. So W is the horizontal distance between left and right lip corner. So H0 is the vertical distance between the upper lip corner and lower lip corner. So H1 and H2 is the distance as you can see in this image. So here is a set of lip features calculated from our video images when speaking the Sinhala phonemes. Now that we have extracted the features, the next step is to do the clustering and subjective analysis so as to generate the Weissim's alphabet. First, we conducted the subjective analysis to prove the Weissim's. For the 40 phonemes, we have 40 mouth shapes. Initially, we have the data set with 40 phonemes, which included 40 mouth shapes. We separate it to 14 vowels and 26 consonants. After analyzing the 14 vowels, we got the 9 distinct mouth shapes, and for the 26 consonants, we got 6 distinct mouth shapes. Secondly, we conducted a clustering mechanism so as to verify the number of groups with a standard approach. From the clustering algorithm, we found 15 clusters together, which means that there can be 15 Weissim's groups. So after considering both subjective and clustering approach, we could conclude that there are 15 groups in the Weissim's alphabet of the Sinhala language. Here are the 9 Weissim's groups to represent the vowel in the Sinhala language. So here are the 6 Weissim groups to represent the consonant in the Sinhala language. So altogether, 15 Weissim groups, and this is considered as the Weissim's alphabet of the Sinhala language. After finding the Weissim's alphabet, the final step is to animate the mouth shapes out from the images. To generate the human model, we have used Make Human software, which is open source. Then we integrate that human model with Blender open source tool to animate the mouth shapes. So 33 parameters were used to generate the mouth shapes. Here in the left-hand side, you can see the 33 parameters used, and in the right-hand side, I have included the generated 15 mouth shapes. So now let's look at the system implementation. Here is the high-level architecture of the proposed lip synchronization model for the Sinhala language. The input will be a Sinhala text. In the flow, we derive the phonetics from the Sinhala text, and after the linguistic analytics of the phonetics, we separate the vowels and consonants. Then we get our generated lip shapes. And if it is a consonant, we combine it with the vowels according to the sound, and we get the Weisim sequence output. And parallel to that flow, we get the audio of the Sinhala text, and we play audio and Weisim sequence together to generate the final output, which is lip synchronization animation. After we input the test sequence as a first step, we derive the phonetic flow. In this step, we conduct 2 major steps, which are encoding and show analysis. On the right-hand side, you can see the part of the encoding schema. So let's understand about the schwa analysis. When we get the phoneme sequence of Makanama word, it shows as this. But when we pronounce that word, it's different from the phoneme sequence that we got. It's like we are not going to pronounce that Makanava. It should be Makanama. To handle this situation, we do the schwa analysis using 8 predefined rules. As the next step, we map the phonemes to voicemes using generated voicemes classes. I used the Papagayo open source tool and modified it to visualize the sound and lip animation together. On the right hand side, you can see the screenshot of the Papagayo tool. Here you can see the inputted sentences. Right after that, it's separated into words, and below you can see the voiceme sequence of the sentences. Move on to the evaluation of the research. In the research evaluation, we conducted two main approaches, which are rating method and ranking method. To evaluate the research, we have three main aspects of the single speech animation model. First one is efficacy of single voicemes, and the second one is accuracy of synchronization of audio and video, and third one is the internal performance of the model. So let's look at the rating method. We chose 6 different single sentences and words from 6 different categories, which are these. We created 6 questionnaires for the 6 categories, where each carrying 10 questions and rating system of 1 to 5 scale. When preparing the questionnaire, word list is selected to address the voiceme's diversity, and sentences list is selected from the UCSC LDRL speech data, and the dataset represent the phoneme diversity. Instructions are given to the participant to rate the videos like this. So consider synchronization of audio and video, and quality and accuracy of the mouth movements when rating to the video. And so rate 5 to the speech animation, which has the same quality as a real human speech, and rate 1 to the worst. Moving on to the result of the rating method, we calculate the accuracy using these equations. So we measure accuracy for a question by getting the score for a question and dividing into the response multiplied 5. Then we added all the accuracies of the questions and divided by the number of questions to get the accuracy of the category. Then we measure the overall rating accuracy by adding all the category accuracies and dividing by number of categories. So these are the results that we got for all the categories. As a conclusion of the rating method result, we got 68.8 accuracy for the model from this number of responses. In this model, you can see for the long sentences, it has got the low result when comparing with the other categories. Let's move to the second evaluation approach, which is ranking method. So we choose 10 words, and for each word it has 3 other words which are similar kind of pronunciation with little variation. So participants need to choose the appropriate word. So questionnaire includes videos of word pronunciation with no audio. So let's look at the result of the ranking method. To measure the accuracy of the question, we divided a number of correct answers by all the responses, and adding the accuracy of the questions and dividing it from the number of questions, we got the overall ranking accuracy. Here you can see the overall accuracy is 70.8 and 8 from the 30 responses. So let's move to the research conclusion. Initially, we started with deep learning approach, and it was terminated due to not having enough video data and unavailability of tools to label them. So we discovered a voiceme's alphabet with 15 voicemes groups for the Sinhala language using clustering and subjective analysis. In the model evaluation, we conducted 2 approaches, which are rating and ranking approaches. Here we got accuracies like 68.8 for the rating accuracy and 70.8 for the ranking accuracy. And also we observed poor performance for the long sentences, and the model is failed to handle speeches which has different speed levels. So moving into the future work, there are few future works which others can consider on. Handle the speech animation of different speed of speech and long sentences with high word transition, and also handle the facial expression when speaking, and also conduct deep learning approach to derive the speech animation. So these are the reference lists I followed throughout the presentation. And thank you.
Okay, thank you, Chashika. So, interesting presentation, interesting research. I think it would be better if you have a small video clip playing the animation. So, so it's now time for the Q&A session. Any questions from the audience? Okay, so now do you have any plans to improve this work further? Maybe so how hard it will be to synchronize a full face. Now we are only synchronizing the lip synchronization, doing the lip synchronization. So how hard it will be to include the other features of the face also, do you think? Have you done any analysis?
Yeah, so can you hear me?
Yeah.
Yeah, so we can I mean animate the facial expression also, but we have to I mean it's some large some different researchers, and there are research conducted on animating that facial expression, only the facial expression also. So one research it's difficult to connect those two things, because when we think about the other part of the face, so we have to think the inside structure of the face also, like inside the mouth. So we have to consider those things also when handling those kind of variations. So but in this research, so I'm planning to like my first blog post to conduct deep learning approach was to label the data. Like, so I'm planning to implement some tool to label the data. So using that tool, so other researchers will be able to use the deep learning approach also if they create some video data. So initially I also created some data about 1 hour or something, but it's not enough actually. Even 1 hour I stopped that because I failed to label the data correctly. So yeah, so that's my plan in the future actually.
Okay. So any other questions? Okay, then thank you, Tashika. So we will show our appreciation for him.
Okay.
Thank you. So we will move to the last presentation in this session. So this presentation is on paper ID 107. Title of the paper is A Framework to Detect Twitter Platform Manipulation and Computational Propaganda. And author of this paper is Nishan Chaturanga Vikramaratne. And Nishan holds a BSc Honors degree in Information Technology from Faculty of Information Technology, University of Marathon. So we will move on with the recorded presentation, and after that the Q&A session.
This is a framework to detect Twitter platform manipulation and computational propaganda, and this is for the paper ID 107. These are the set of authors who presented the paper, and our supervisor is Dr. Upeksha Ganegoda from University of Marathon. So for starters, I'll start with what is platform manipulation. It is refers to the use of Twitter to mislead others and disrupt their experience by engaging bulk, aggressive, or deceptive activity. This activity includes, but is not limited to, spam, malicious automation, and authenticating account abuse like fake accounts. So as per the Global Disinformation Order report provided by the Computational Propaganda Research Project, They have identified that social media manipulation campaigns which have taken place in 70 countries, which is up from 48 countries in 2018 and 28 countries in 2017. In each country, there is at least one political party or government agency using social media to shape public attitudes domestically. So here also see the different demographics in each of those mentioned years. You can see that there is overall 150% increase in the countries using organized social media manipulation campaigns over the last 2 years. So to tackle this problem, the framework that we have come up with is this. So here module 1 corresponds to creating keywords, extraction and collecting relevant news. So what it does is collect this set of keywords from a tweet given to this framework and use that set of keywords to collect the relevant news or relevant tweets from the Twitter API. And all those collected news or tweets will be feeded into this module 2, deception and automated account detection, and also for module 3 and also to module 4. There is a dependency between module 3 and module 4, which gives some parameters to module 4 from module 3. So first of all, keywords extraction and collecting relevant news. So for this, a corpus was created which consists of more than 100,000 tweets collected via Twitter API and Kaggle. So this is what we wanted to do is to make it as generic corpus, because existing corpora are built with tweets either domain specific or have less data. So we pre-processed those collected tweets. After pre-processing, you can see that we have reduced all those unnecessary words. So for the keywords, as I mentioned earlier, we need keywords to get the or the query the Twitter API so that we can get the relevant news or relevant tweets from the Twitter API. So important keywords in a tweet are such as person names, locations, organizations, dates, and other nouns likewise. So the design of the module is as follows. The claim tweet or the initial tweet will be input as a parameter to the algorithm, and after the pre-processing text, we will take the keywords. To do that, we do NER tagging, person names, locations, organization, dates, nationalities are filtered using that, and Stanford Core NLP toolkit was also used to get NER tagging since it has 7-class model tagging. So this and Stanford Core NLP toolkit is a free open source toolkit that we can use. TF-IDF statistical method will be applied on the remaining words using the corpus. Since there could be important words that had been missed in the previous steps. So after the extracting those keywords, then we do synonyms. So because using Gensim word to egg, because some same news can be posted by using 2 different words. Similarity index had been determined using a statistical experiment. So after we extract these keywords using the mentioned methodologies, we use the Twitter API to query, and then we get set of tweets referencing that specific context. So to evaluate this model, we use Turing test. Turing test is so we use a set of participants, and then we give them the tweet and the extracted keywords from that tweet, and they will score the output based on the similarity or the relevancy of that specific tweet. So we use several type of participants to do this, and we have observed that successful percentage is 63.36 using this method that we have used. And when it comes to deception and bots, first of all, let me give a brief background regarding this. On 3rd of January 2020, United States drone strike near the Baghdad International Airport killed Iranian Major General Qasim Soleimani. After the incident, Iran strike back with 15 missiles launching on US targets in Iraq, but there were no casualties. A fake news was propagating through the social media, saying that at least 80 Americans were killed. So this is example of social media information operation carried out by Iranian government. So to accomplish such kind of scenario, there are multiple kind of bots that they use. So puppet bot, as the name implies, are controlled by a human. Then amplifier bot retweets and spread that tweet into a wider audience. And then approval bots come and react on those tweets, so they will have higher number of likes. So the people like you and me will consider them as credible news. So to identify these bots, you have to keep an eye out for number of links, number of hashtags, and they tend to make grammatical errors. And also the context is also everything, because the tweet is usually these mass media campaigns are targeted toward some important event or important news happening around the country. So to tackle this problem, we have, first of all, we are trying to identify the deception. So to identify deception or the fake or the authenticity, we have used two data sets to train the models. We used logistic regression, multinomial naive Bayes, and count vectorizer together with TF-IDF and different their combinations to come up with a better solution. We have identified that using different data sets, the output is different. So that means depending on the domain, the authenticity could be different, right? So meaning that I would be tweeting authentic content on another one domain and false information for another domain. So there could be instances like that. That is why the output is differencing as we perceived. The word count contributes the most positively to being non-credible is incredible, as you can see. And the word count contributes most positively for being in the credible, it is arrested. So likewise, you can get a number of frequencies and what are the words that are contributing uh, to distinguish these tweets from being credible or non-credible. Then what we do is, obviously, of course, we give what is the credibility of the tweet first of all, and then we use the most used terms in non-credible use, and then we subtract most used terms used in credible news. So what we get is the most used terms appearing only in non-credible news. Then we look for these words in the attributes of a tweet or a user account. Say the user account has description. So if one of these words are appearing in the description of that user account, we assume that that account or that tweet could be a bot account, could be tweeted by a bot account. So that is what this domain linking part do. So let me just tell you that the first feature, this feature that we derived using this most used terms in non-credible news alone increased the model accuracy by 1.36, and all the other engineered features resulted in 2.69 increase. So these are the created features. So you can see there are some features called binary features. So as an example, description binary. If the description binary is 1, that means the description contains one of those mentioned words appearing in non-credible news, right? So the NA features are null features. So likewise, we can identify what are the different features and what what contributes to the output the most, right? So after creating the credibility or after getting the bot or non-bot output, we move on to creating impact and the credibility. So to create the impact, we see that the impact is usually negative or positive. So based upon that, we create agreement score, dividing number of positive followers responses by total number of followers responses. So these positive followers responses are created using sentiment analysis. And apart from the sentiment analysis agreement score, we use another feature called the news category. Again, this is derived from a machine learning techniques that we can put a tweet into different categories like sport, political, etc. After creating these features and set of features available in the dataset like followers count, we use a clustering algorithm to divide these user counts into 5 different credibility baskets. So if a tweet comes as 1 or an account comes as 1, that means that user has less credibility. If a tweet comes as 5, that means that account has a higher credibility. So yeah, as I mentioned earlier, this is clustering algorithm. Here also see the same methodology in a more descriptive manner. So as you can see, we have identified that 70% of overall accuracy has been generated using this complete module, which is the credibility module. So as you can see, these are the categories that we observe in the tweets, and these are the tweet users. So as you can see, if it is CNN, you will get around 4%, right? So if it's a person or individual entity, you will get like 3 to 2 kind of credibility rating, right? And when it comes to the forecast, what we do is we are trying to get hold of a number that this amount of tweets will be in the future. So at the start, the tweeting regarding one specific news event could be 100. So what we are trying to do is at the end of this event or this social media phenomena, there would be this amount of tweets, like say for an example, 200,000 tweets will be available in the network if once this event is over. So to forecast that, we use recurrent neural networks. We collect data in different timestamps, and then we feed that data into a recurrent neural network. So to do that, we divide the initial data set provided by the module 1, and then we divide them into different timestamps. 1 day, 1 day timestamps, timestamp baskets, and then we get input those tweets into the recurrent neural network, which is LSTM, and then we try to come up with the number that this event could be reaching this amount of tweets. So as I mentioned earlier, so this implementation was LSTM. We can also more extend this module to be generalized prediction model through layered stacked LSTM. So these are the features that we are using. As you can see, this categorical component feature ratio comes from the module credibility module, and also this positive implementation ratio is also coming from that. So yeah, so there are 14 different features that we feed into the neural network. So at the end of the day, we observed that there are low number of error matrices. These are also that we observed that these are very low comparing to what we are seeing at the current models that we have observed in the literature. So all those 4 modules are at the end creating different outputs. So these outputs will be guide the user to get a educated decision on whether to trust or disregard this content that he has come across. So yes, that will be our research. Thank you.
Okay, thank you, Nishan. Now it is the time for the Q&A. So, any questions from the audience? Okay, Nishan. So you have mentioned that you have worked with them with some set of features. As your paper says, it's 24 features. You have created 24 features from the data provided by the Twitter API. So, on what basis have you defined these features?
So the basis is actually the research of the paper, because what we think is if there could be a word or a phrase that is appearing in non-credible news, so and that same set of words are appearing in the data provided in the Twitter API, say for an example. So you usually put a description in the Twitter profile. So if your Twitter profile contains any of those words, so this user could be targeting or using the Twitter to mislead others. So based on that assumptions, we created the features, and also we used null features, which means that if you don't have a profile picture, there could be a high chance that you could be a bot account, right? So if you don't have a description or a location mentioned in your tweet profile, there's a high chance that your profile could be something inauthentic account. So that is the basis that we took into account when we are creating those features.
Okay, thank you. So, any other questions? It seems we don't have any other questions. So thank you, Nishan. So we will show our appreciation for him.
Thank you very much.
Okay, thank you. So that concludes the presentations of our session. So thank you all the presenters and for those who have participated in this session. So I will now hand over this session to our compeer. So over to you, Dushani.
Thank you, Dr. Telene. So the session ends here, and next up we have the keynote speech, the fourth keynote of the conference, which will start at 2 o'clock. So you can join the keynote in Microsoft Teams. You can click on keynote 4 there. So have a good day and take care.